Welcome back student to yet another lecture of the pipe flow. In the last lecture we derived the Poiseuille's law. The Poiseuille's law is Q is equal to pi d to the power 4 into delta P by 128 mu L, where L is length of the pipe and delta P is the pressure drop. So, we have been able to relate the pressure discharge pressure drop with the discharge. So, proceeding forward, we will now see what if the gravity was also present, and that if it can be added to the pressure. All right. So, if you earlier our pipe was horizontal, there was no gravity, but right now the equations of motion will change, because then there will be another, this w sin theta, that is pi r square L sin theta, w sin theta, this is in multiplied by gamma pi r square L sin theta will be another component that will be acting in this direction. All right, because of which our analysis will change a bit, but what happens, it instead of delta P we are going to get components like minus rho GL sin theta in the equation number 1 when we are going to calculate the velocity, minus rho GL sin theta here, and the Poiseuille's law will change where minus rho GL sin theta. If you want to verify, see this is valid for all the angles, right. So, if you put theta is equal to 0, you see this term will vanish, this term will vanish, and this term, because sin theta sin 0 is equal to 0. It will be same as what we have derived before. So, you can also try to remember these equations. At least Poiseuille's law you remember, that is quite important. All right, with or without the change in angle, if the gravity is there or not with the sloping pipe. So, these are the generalized equation. All right, good. So, now we are going to solve a question which says that an oil with viscosity of 0.4 Newton second per meter square and density of 900 kilogram per meter cube flows in a pipe of diameter 0.02 meter. What pressure drop is needed to produce a flow rate of 2 into 10 to the power minus 5 meter cube per second if the pipe is horizontal with x is equal to 0 and x2 is equal to 10 meter. All right, that is the first question. Another question is, how steep a hill must the pipe be on if the oil is to flow through the pipe at the same rate as above with delta P is equal to 0. And the third, for the conditions of part B, this one, if P1 is equal to 200 kilopascal, what is the pressure at section x3 is equal to 5 meter where x is measured along the pipe. So, this is the question that involves the use of Poiseuille's law, all right, and also involves the last equations that we have seen, what happens if the gravity was present. So, to solve this, we will solve this in a white screen. All right. The solution to the first one. So, if the Reynolds number is less than 2100, the flow is laminar, correct. and the equations derived before are valid. Correct? Since the average velocity is v is equal to q by a. All right. So q is 2 into 10 to the power minus 5 and area is pi by 4 into 0.0220 whole square, and this comes to be 0.0637 meters per second. And how do we write the Reynolds number? Rho Vd by mu, and on putting this you will get Reynolds number. With this velocity we are going to get Reynolds number of 2.87. This Reynolds number is less than 2100, which implies hence the flow is laminar and L is equal to x2 minus x1 is equal to 10 meter. Alright, so first we found out the velocity, check that using the Reynolds number if it is laminar or not. Yes, it was laminar, and the pressure drop was P1 minus P2 is equal to 128 using the Poiseuille's law. All right. So we are now going to substitute that. So delta P, I will rewrite the equation, is equal to P1 minus P2 is equal to 128 mu LQ divided by pi d to the power 4. All right. So delta P is going to be 128 mu is 0.40 into 10 into 2 into 10 to the power minus 5 divided by pi into 10 to the power 4. So pressure drop is going to be 20371 Newton per meter square or 20.4 kilopascal. This is the pressure drop that we found out using the Poiseuille's law. The second part says if the pipe is on a hill of angle theta such that the pressure drop P1 minus P2 is equal to 0. All right. So for this we use modified Poiseuille's law, and we can write, because delta P is equal to 0, so we can use sin theta will be minus 128 mu q divided by pi rho g into d to the power 4. So sin theta is going to be minus 128, this is 0.40 into 2 into 10 to the power minus 5 into pi into 900 into 9.81 into 0.020 to the power 4, and theta is going to be approximately minus 13.34 degrees. So in part A we use simple Poiseuille's law. In the second one we use the modified Poiseuille's law. All right. Now the third part says that with P1 is equal to P2, the length of pipe L does not in the flow rate equation. All right. So this is a statement of the fact that for such cases the pressure is all along the, see, for part B we said there was no pressure drop, right? That is correct. So that means the pressure is constant all along the pipe. All right. Since delta P is equal to 0, P1 minus P2 is equal to 0, so P1 is equal to P2, and P2 is equal to how much? Sorry, P1 is equal to 200 kilopascal. Sorry, or yes, P3. Sorry. Therefore, P3 is also going to be 200 kilopascal. Since delta P was 0 in part B. Very simple, because there was no pressure drop per unit length. So the pressure would be the same as what is at 0.1. All right. So we finish this one here. So in the previous question we have seen the application of Poiseuille's law and also the modified Poiseuille's law in presence of the gravity. With this point we move forward to our second way of finding the finding the laminar flow in the pipes for fully developed flow. But before that we should revise some basic mathematics for revision, and this concerns our mathematical operator. For example, there is an operator called del operator, which every one of you know. It is del del x, del del y and del del z. Now the Laplacian operator is del square, that means it's del square del x by del square by del x square, del square by del y square and del square by del z square. Gradient operator, it's del p, it's del p del x, del p del y, del p del z. All right. There is a vector gradient, that is del u, del v, del w. There is a divergence operator, that is del dot u, that gives del u del x, del v del y and del w del z. These are all basic mathematical equations that you know from before. There is one directional derivative, that u dot del, it becomes u del del x plus v del del y and w del del z. All right. So with this thing we are proceeding ahead for derivation of the laminar flow through pipes using the Navier-Stokes equation. All right. So, the general motion of an incompressible Newtonian fluid is governed by the continuity equation and the conservation of mass. This continuity equation is written as del dot u is equal to 0. This is continuity equation, whereas the momentum equation is written as this. Or Navier-Stokes equation. All right, and this is equation number 8. So, you should remember that for steady fully developed flow in the pipe, the velocity contains only an axial component, which is the function of only the radial coordinates r that we have talked in the beginning of this chapter itself, right. So, for such conditions, the left hand side of the momentum equation becomes 0 because it is steady, correct. This is equivalent to saying that the fluid experiences no acceleration, it flows along. So, convective acceleration and everything is 0. This is acceleration, local acceleration, this is convective acceleration. Okay. The same constraint was used in the previous section when we considered F is equal to ma for fluid cylinders. So, left side of the Navier-Stokes equation becomes 0 because there is no acceleration in the flow. Therefore, if we write with g as minus g in terms of vector, the Navier-Stokes equation, so the continuity equation will be del dot v is equal to 0, and the right hand side can be written as delta p plus rho gk plus mu del square v, correct. Now, the flow is governed by the balance of pressure, weight and viscous forces in the flow direction. All right. In cylindrical coordinates, we can simply write, so del p is del p del x plus rho g sin theta, whereas mu in radial direction 1 by r del r into r del u by del r. So, this is the using the Navier-Stokes equation, of flow through the pipe equation of flow through the pipe for a fully developed laminar flow. Okay. So, here the assumptions and the results are exactly same as the Navier-Stokes equation, which is derived from the Newton's second law. All right, just written in a more differential form. Now, the third way I said was dimensional analysis. From your dimensional analysis module, you remember that pressure is a function of V, L, D and mu. All right. So, if we take delta P by L is a function of V, D, mu, or yeah, this is let's take K is how much? 5, R is, so 1, 2, 3, 4, 5. So, K is 5 and R is 3, right. So therefore number of dimensionless terms will be k minus r, that is 2 dimensionless term. So pi 1 and pi 2. We get this using dimensional analysis. All right. So using dimensional analysis we get this result. Now assuming that the pressure drop is proportional to the length, so we say that d delta p by mu v is directly proportional to the length, so it becomes c into L by d. All right. So from here, because you might not be so d delta p by mu v is some function of L by d, but we say proportional to the length, so we write constant c into L by d, this equation. Therefore we can write delta p by L, L we bring this side, other parameters we take that side, okay. It becomes c mu v by d square, or q is equal to area into velocity. All right. So area is pi by 4 d square, therefore we will get pi by 4 into c delta p d to the power 4 by mu L as this equation. All right. Now you see there is some constant called c. We are going to look into something here that is called Darcy's friction factor. If we rewrite the Poiseuille's law was pi d to the power 4 delta p by 128 mu L, correct? Therefore delta p could be written as 32 mu L v by d square, all right, in terms of velocity. Now if we divide both sides by this side, so this is in terms of q and this is in terms of v, so this is also a form of Poiseuille's law. If we divide both sides by dynamic pressure, like half rho v square, so delta p by half rho v square will be 32 mu L v by d square divided by half rho v square. So this will be, this half goes up and becomes 64, and this we can take out mu by rho v d into L by d, and this mu rho v d by mu is Re. So basically we can write delta p by half rho v square is equal to 64 by Re into L by d. All right. So you see, we would see later that this 64 by Re is termed as Darcy friction factor F. Darcy means this is for the laminar flow. So this is often written as delta P is equal to F into L by d rho v square by 2. With this equation number 10 analogy, we say that Darcy friction F for laminar fully developed pipe flow is given by 64 by Re, and this is Darcy friction factor F for fully developed laminar flow, and this is, you must remember this. All right. This is equation number 11. So now in terms of wall shear stress, if we use equation number 3, F can be written as, so equation, if we use this, FL by D into rho V square by 2, if in terms of wall shear stress using equation 3, we will get F is equal to 8 tau W by rho V square. This is quite simple. Do it as your homework. All right. If you have any problems, you can ask that to me in the forum. And this is equation number 12. It's just a matter of equating to obtain this in terms of wall shear stress. All right. So I think this is a nice point to stop this lecture, and I will see you in the next lecture, where we are going to continue the topic of energy in fully developed laminar flows. All right. Thank you so much for listening, and I will see you in the next class.